Welcome to this explainer. Today we're jumping right in to decode the dense but honestly fascinating engineering standards of API Specification 5L. We're going to be looking specifically at annexes E, F, and G. Now, this isn't just a bunch of paperwork. This is the exact framework that dictates how we keep incredibly dangerous, highly pressurized materials safely contained right beneath our feet.
So, we've got to ask this critical question right out of the gate, because the stakes for pipeline integrity are just sky high. We're talking about massive infrastructure carrying highly volatile hydrocarbons, natural gas, and CO2, all under immense, unrelenting pressure. Literally, one tiny flaw can lead to a catastrophic rupture. So how on earth do engineers sleep at night knowing these pipelines are under that kind of extreme stress?
Well, to answer that, we look straight to this standard API Spec 5L. It essentially acts as a comprehensive, strictly enforced shield against disaster. It's actually incredible to see just how uncompromising this living, breathing document really is. It dictates the exact metallurgical and mechanical requirements these pipes have to meet before they ever see the field. Today, we're focusing on the highly technical annexes that act as the enforcers of this entire standard.
Here's our roadmap for today. We'll be looking at ensuring pipeline integrity, finding flaws through non-destructive inspection, evaluating imperfections and defects, connecting pipes with coupling standards, and finally, stopping ductile fractures.
Okay, let's kick things off with Section 1, ensuring pipeline integrity. Which brings us right into Section 2, finding flaws through non-destructive inspection.
You can basically think of this as medical imaging, but for pipelines. We use core NDT, or non-destructive testing methods, things like electromagnetic flux leakage, ultrasonic testing, and radiographic X-rays. This lets us peer deep into solid steel without actually cutting it open or damaging it in any way. And you don't just hand these highly advanced tools to anyone off the street. The standard firmly mandates that these inspections are run by certified Level 1, 2, or 3 personnel. It is a highly controlled, incredibly precise discipline.
And the standard leaves absolutely no room for guesswork here. The manufacturing method actually dictates your diagnostic tool. For instance, if you're dealing with an electric welded pipe, or EW, you must use either an electromagnetic or an ultrasonic method, or maybe a combo of the two. But if you switch over to submerged arc welded or SAW, well, suddenly electromagnetic testing is completely out of the picture. Instead, ultrasonic testing becomes the mandatory requirement, and radiography is only brought in if the manufacturer and the purchaser specifically agree to it.
Moving right along to Section 3, evaluating imperfections and defects.
Just like a doctor has to calibrate an X-ray machine before a scan, pipeline engineers use an IQI, an image quality indicator. This ensures their pipeline X-rays are picking up the exact right level of detail. The API standard requires these wire-type IQIs to be used dynamically. For dynamic methods running at production speeds, this tool has to verify the sensitivity of the setup at least once per 4-hour operating shift. And get this, if your image quality fails to meet the strict criteria, every single pipe you inspected since the last successful check has to be completely tested all over again, no exceptions.
Now, it's really fascinating how they draw a strict, uncompromising dividing line between what is just an allowable surface irregularity and what is a mandatory defect. An acceptable imperfection might be a tiny gas pocket or a minor slag inclusion. Those are just natural byproducts of welding. And as long as they fall within the strict dimensional limits detailed in the API tables, they don't compromise structural integrity. On the flip side, things like cracks, a lack of complete penetration, or metals just failing to fully fuse, those are universally classified as defects. They cross the line. That means the pipe has to be aggressively repaired by grinding and welding, or honestly just rejected entirely.
Let's shift gears now to Section 4, connecting pipes and coupling standards.
Because, let's be real, a pipeline is literally only as strong as its weakest joint. You could have the most perfectly manufactured, heavily inspected pipe in the world, but it means absolutely nothing if the coupling holding it to the next pipe fails. When assembling these pipes, there is a very deliberate engineering difference between a basic hand-tight makeup and a fully locked-in, power-tight makeup. The threading and the overlap are designed to create a completely impenetrable seal, and the standard ensures these couplings are absolutely free from blisters, pits, or really any imperfections that could break the continuity of the thread. To give you a sense of the scale and the extreme tolerances we're dealing with here, just think about a massive 20-inch outer diameter pipe. The coupling for that pipe alone has a calculated mass of roughly 79 pounds.
That is an incredibly heavy, meticulously machined piece of steel, and its sole job is to handle massive operational pressures across decades of continuous use. So yeah, definitely not something you want to drop on your foot.
And finally, we hit Section 5, stopping ductile fractures.
Because despite all our non-destructive testing and heavy-duty couplings, external forces like an earthquake or heavy machinery accidentally striking the pipe can still cause a breach. To stop a crack from just unzipping miles of natural gas pipeline at astonishing speeds, we measure its toughness using Charpy V-notch or CVN impact testing. The CVN absorbed energy is basically a measurement of how much absolute punishment the steel can take before it tears. The material has to possess enough inherent toughness to arrest a running crack, essentially stopping it dead in its tracks before it travels far down the line.
And here is the magic number, 85%. According to the standard for CSVN impact tests on pipe bodies under 508 millimeters, the average shear fracture area has to be greater than or equal to 85% at the specified test temperature. This is crucial because it ensures the steel behaves in a ductile, forgiving manner. It tears safely rather than just shattering like glass. This metric right here is exactly what stands between a safe, localized pipe failure and a massive infrastructure disaster.
So how do engineers figure this out in the real world? Well, using the European Pipeline Research Group, or EPRG, guidelines, they follow these really strict steps to calculate the exact energy absorption required to arrest a ductile fracture. First, determine the minimum CVN value. Then, validate it against real-world operating parameters. Like, this specific EPRG approach is valid for pipelines with maximum design pressures not greater than 10.0 megapascals. And if the design pushes outside those bounds, maybe dealing with higher pressures or different gas compositions, engineers can't just guess. They literally have to conduct full-scale burst testing to physically verify that the pipe has the fracture arrest capability required.
API Specification 5L isn't just red tape, folks, it's a living shield. It provides the exact dimensions, the specific non-destructive tests, and the complex fracture mechanics needed to build our modern world safely. But as we start transporting denser materials like liquid CO2 for carbon capture and push these pipelines to their absolute engineering limits, it really makes you wonder, are our current standards tough enough to contain the invisible, massive forces of tomorrow's energy grid? It's definitely something to think about the next time you see one of those pipeline markers on the side of the road. Thanks for joining me on this explainer.